Hello, welcome to this lecture of the course Elements of Mechanical Vibration. The previous lecture deliberated different damping models, and in today's lecture we will devote some time to energy methods of deriving the governing equation of motion. So, if you remember the steps in carrying out vibration analysis on any mechanical system involves first converting the system from the physical system to a simplified vibratory model, and from that simplified vibratory model, like a spring mass dashpot system, we derive governing equations of motion by using Newtonian approach. That by default or the most convenient way, because we know how to get a free body diagram, identify what are the interaction forces, and then apply Newton's second law. So, that method is straightforward and works well most of the times, but it also has some limitations. When the system becomes complex, it is hard to keep track of the sense of the forces which are acting on the free bodies. So, an alternate and more elegant method, so to say, is energy method, where we make use of the energies in the vibratory system to get the governing equations of motion. So, we shall now focus on few alternatives that we have, but I mean these alternatives are a part of energy based methods. So, the first approach is, of course, once we identify the total kinetic energy and the total potential energy of the system, one way to arrive at the governing equation of motion is the average energy principle, wherein the average kinetic energy and average potential energy of a vibratory system is equated, and for an oscillating system this applies, that average kinetic energy is equal to average potential energy. You can imagine a simple oscillating pendulum. You can find out what is the average kinetic energy of the pendulum in a cycle and what is the average potential energy. If you equate it, you will get the governing equation of motion. The other method is principle of conservation of energy, wherein the total energy is of the system is constant, or alternatively put, if you take the the derivative, time derivative of the total energy of the system, that is equal to 0. So, either you write as T plus V is equal to constant, or the time derivative is 0. Once you write this equation, by the solution of this equation will lead you to the governing equation of motion. The other method, which is in a way similar to the first one, is to equate the kinetic maximum kinetic energy and maximum potential energy. And the last among all these energy based methods, which is much more comprehensively used and is most elegant one, is applying Lagrange's equation once we have again identified the expressions for the total kinetic energy and total potential energy of the system. So, the Lagrange's equation, if it is derived, looks like this. So, it involves derivatives with respect to the generalized coordinates. For a single degree of freedom system, of course, the equation becomes very simple, in that there will be only one degree of freedom. So, only one generalized coordinate may be x. So, dou t of dou t over dou x, dou t of dou x minus dou t over dou x plus dou v by dou x is equal to 0. So, that becomes the Lagrange's equation, and if you take these derivatives, finally you will get the governing equation of motion. So, we shall of course apply one or two of these equations in some simple examples to get the governing equation of motion for a vibratory system. As the number of degrees of freedom increases, most of us find it convenient to apply the Lagrangian equation, and then you can get as many number of governing equations as there are number of degrees of freedom or these coordinates denoted by I in this equation. So, with this background, let us look at how we can apply these equations of I mean these energy methods to get the governing equation. Okay, now let us take an example of application of this energy methods. So, the example here is that of a vertical bar of mass m. So, a uniform rod of mass m and length L. Okay. This bar is connected to two springs at these locations. So, location A and location B, these are the two springs which are keeping the rod vertically straight. Okay. Now, what we want to do is to look at its dynamics once it is disturbed from its equilibrium vertical position. Okay. Now, just although we are going to implement the energy method to explore the governing equation of motion and subsequent expression for the natural frequency, just for the sake of comparison, I would like to quickly analyze this problem using the conventional method of Newton's application of Newton's second law. So, we all know that it would pertain to getting the forces located on this bar as a free body. So, the moment this bar moves about the fulcrum here at the base, so this is the fulcrum, the hinge about which the bar is expected to rock. So, the moment you have a small angular displacement theta about the mean equilibrium position, which is vertical assumed here, the restoring forces quickly act on this particular bar, and this restoring force obviously is going to be the stretch in the spring. That stretch is obviously going to be L2 into theta, because that is the length at which the spring is located. So, the stretch with the angle theta made is going to be L1 theta, and the restoring force then obviously will have to be K into this is going to be L2 theta, and this spring is going to get compressed, this spring is going to get stretched for clockwise theta motion, and therefore, at this point of connection at point B, the restoring force is going to be again in this direction, because this compressed spring is going to restore the bar to the equilibrium position, and then the restoring force is going to be K into L1 theta. That is quite straightforward. So, if you now apply the Newton's second law, the summation of all the moments about O, which is this point, is the inertia times the angular acceleration. So, theta and theta dot are assumed clockwise positive. Now, obviously, I can write this as I theta double dot equal to summation of all the moments are now going to be k into L2 theta times L2, that is the arm length, and then to that I would add the second moment due to this particular spring. So, that is going to be k into L1 theta into L. Okay. However, it is obvious that if the bars rotates like this, there is going to be the gravity which is going to also jump in the set of forces and moments. So, what we assume that the bar being uniform, the total mass can be assumed here at the at the center of this total length, and then this mass or the gravity mg is going to act at the center, and this arm length for this arm length for the moment of the gravity force is going to be now negative, because these moments are all become or are going to be negative, and then the gravity is going to generate a positive moment, right, because theta is assumed positive this side. So, the moments in the direction of the angular acceleration are on the right hand side going to be positive. So, plus mg into the into this length, right. This is the distance at which the mg force is going to generate a moment. So, that distance obviously is L by 2, because L is the total length of the bar, L by 2 times sin theta. Okay. This is going to be sin theta, which I can approximate as theta for small angular displacement, and this is all the time we therefore have to use the assumption of small amplitude vibration, so that these equations are valid. So, if I write this equation that I am getting from the application of the second law, I can write this as I theta double dot plus k into L1 square plus L2 square into theta, and then of course, I will have to write this as minus mg L by 2 into theta is equal to 0. So, this actually is now my governing equation of motion. Here the gravity is accounted for, because the rod is assumed vertical. If it is assumed horizontal, so that the bar swings in the horizontal plane, then the gravity will not play any role in the moments generated trying to restore the original equilibrium position. Only the springs will come into action, and then the natural frequency obviously in the if the rod is assumed horizontal and the motion is in the horizontal plane, then of course the natural frequency will be k L1 square plus L2 square divided by the mass moment of inertia of the bar. Now, the mass moment of inertia which about this end of the bar can be written as ml square by 3, and if m is the mass of the entire bar, L is the total length of the bar, where L1 and L2 are the connection points, the positions of the connection point with respect to hinge. So, if we take the motion in the horizontal plane without gravity appearing or effective, then this is the expression, but in the presence of gravity, this additional term will be included in the numerator. Okay. This is basically the quick approach of getting the natural frequency using Newton's law. Let us focus on the energy method. So, as we discussed, the energy method will involve you first finding out the expressions for the kinetic energy and expression of the potential energy. So, the kinetic energy of various elements in the vibratory system, if we want to know, obviously the springs are assumed massless. So, the first assumption here we will make is that the springs, both this one and this one, they are massless. Okay. You can include the mass of the springs, and then of course, the expression will change, but we will take another example later to bring in the mass of the springs into the governing equation. But here let us assume the springs massless, and then the natural but then the kinetic energy expression is based on the kinetic energy stored in the motion of the uniform rod. So, that obviously is going to be half mass moment of inertia velocity, in this case theta dot whole square, that basically is your kinetic energy expression for the rod. And the springs are meant to only store the strain energy. So, the expression for the potential energy, in this case it is going to be strain energy stored, and that sorry, let us keep taking. So, the expression for the potential energy V is going to be the energy stored in the first spring. So, maybe this is your okay, this is the first spring at the top, let us say K, and you know the strain energy stored in the stretched spring is half K x square, where x is the strain in the spring. So, in this case the strain or elongation in the string in the spring is L2 into theta, that is our extension in the spring which is here located at L2 distance from the hinge. So, square of this basically is the strain energy of the first spring. The strain energy similarly of the second spring is going to be So, the strain energy of the second spring is K into L1 theta whole square. Okay. But again, if we assume the rod to be vertically oriented, then in that case as the rod oscillates or leaves its equilibrium position, then the original energy, potential energy will also get reduced, because the center of mass is going to shift a bit. Okay. So, what we are saying here is that if this uniform rod let us say changes its position here. So, if this bar now changes its position from the vertical position, I am going to basically show the change in its center of gravity point. So, this gets shifted by this angle, and the drop in its position vertically is going to be for a small angle theta motion here, and then of course, this will be L by 2. Okay. See, the position of the center of mass is L by 2. This is going to be L by 2 minus L by 2 cos theta, is not it. So, this distance is going to be L by 2 cos theta, and the drop in the position is going to be L by 2 into 1 minus cos theta. So, the drop here is minus mg L by 2 1 minus cos theta. Okay. And how do I write 1 minus cos theta for small angle approximation? 1 minus sin square theta raised to power half, and then I can expand this and approximate this as 1 minus half theta square. We know that through ignoring higher order terms, and then of course, this finally turns out to be half theta square. 1 minus cos theta is approximated by half theta square. This approximation is of course valid for small angle theta. And then I can rewrite this as half k L2 theta square, or maybe I can write this as I can write this as half k L1 square plus L2 square and theta square minus mg L by 4 theta square. because 1 minus cos theta is replaced with half theta square. So, this is your potential and energy expression, and now if I want to apply energy method, one obvious option that I have is that through conservation of energy I can simply write the total energy remains constant, which is the another way of writing it is ddt of V plus T, or total energy, is equal to 0. So, you can find out the relevant expression using this approach, but I can also use another alternative, and a more elegant and more commonly used approach is to apply or use Lagrange's equation. Now, the Lagrange's equation that we wrote in the previous slide read like this: dou t of dou t by dou q I dot minus dou t dou q I plus dou v by dou q I equal to 0. Now, this in this equation q I is basically the generalized coordinate. Now, in our case this generalized coordinate is theta, and therefore, this equation would read dou t of dou t over dou theta dot minus dou t over dou theta plus dou v by okay. Now, in our case this equation would reduce to, because there is only one generalized coordinate, that is theta, I can write this as dt by dt by d theta dot minus so I can write this equation because theta is the only coordinate in question. So, this is going to be dt by d theta dot minus dt d theta plus dv by d theta equal to 0. Now, if you take or substitute these expressions, we have this expression for the kinetic energy and this expression for the potential energy, then I can write let us take the first term, that is going to be d dt of derivative of this with respect to theta dot is going to be just I theta dot, and minus this term. Obviously, if you take the derivative of the kinetic energy with respect to theta, it is going to be 0, and then plus dv by d theta is going to be k L1 square plus L2 square theta minus mg L by 4 mg L by 2 theta. Okay, that is the expression we have equal to 0. Now, further I can write this as I theta double dot as the derivative with respect to time plus this expression of k L1 square plus L2 square minus mg L by 2 theta equal to 0, and that gives me, this is in our standard form, that mx double dot plus kx equal to 0. This one is in the similar form, and the natural frequency of angular vibration or angular oscillations is now going to be k L1 square plus L2 square minus mg L over 2, and of course, I can write I here, okay, and that would be similar to this expression that I got using the Newton's law, okay, and we expected to get the same expression irrespective of the method of getting the governing equation and the natural frequency. So, this is the governing equation of motion, and the natural frequency is obtained as you see here. Things are fine, and there are some interesting things that we can obtain from here. Maybe if you want to use the second approach of d dt of v plus t equal to 0, I can take the derivative of all of them. So, v plus t, and then in that case what I get is k L1 square plus L2 square, or let me write them with a different. So, this gives us what, k L1 square plus L2 square theta dot minus mg L over 2 theta dot plus I theta dot theta double dot, okay, equal to 0, which ultimately gives me the expression. So, what happens is theta dot cancels out throughout, and I am left with the equation I theta double dot plus k L1 square plus L2 square minus mg L by 2 equal to, sorry, this whole bracket is multiplied by theta equal to 0, which actually gives me, comparing with the standard form of the equation of motion, omega n is equal to square root of k L1 square plus L2 square minus mg L over 2 over I, okay. And in all of these equations, I can be replaced with ml square by 3, that is the value of the mass moment of inertia of a bar of mass m of length L about its end, okay. Okay. Now, as I said, this up to this point is fine, but there is an interesting thing that we should learn from this particular example is, although the expression for the natural frequency we have obtained is k L1 square plus L2 square minus mg L by 2 over I, which is now being replaced with ml square by 3, okay. Okay. Now, the expression in the of the natural frequency has the numerator, which is k L1 square plus L2 square minus mg L by 2. This numerator can in some case turn out to be 0, depending upon the value of k relative to the mass of the rod, okay. Just imagine that the springs are so floppy and so light in the sense of its spring rate that in comparison the mass of this bar is so large that if you disturb this slightly on either side, and if the springs do not provide reasonable restoring force, it is quite possible that the moment of the gravity acting on the bar will pull it continuously without going back to its mean equilibrium vertical position. Okay. So, let us look at those eventualities by looking at 2 or 3 possibilities. One possibility is that their relative values are such that this numerator is greater than 0, then there is no problem in the sense that the natural frequency will be some numerical value, and obviously the bar will keep on swinging back and forth under the action of the restoring forces and the inertia of the bar. Depending upon the relative values, what is going to happen is that the time period of this swinging motion about the mean vertical equilibrium position, that time period will change based on the relative values of k and the mass of the bar. Okay. But it will oscillate about this hinge, that is for sure. Okay. Let us look at what happens if the equation that we discussed, that is I theta double dot plus this entire bracketed term times theta equal to 0. Now, this bracketed term was basically the numerator here. Okay. So, now what we do is we take the case where k L1 square plus L2 square minus mg L over 2 is actually equal to 0, that is the threshold point. So, if this is greater than 0, this expression, then we know that it is going to be an oscillatory system, the system will have natural frequency as given by this, no problems for that. But there is one threshold point here, that if this term is equal to 0, that then what happens? Then basically what we get is I theta double dot equal to simply 0, right. So, the expression that we now need to solve, or the equation that we need to solve, is theta double dot equal to 0. Now, what is the solution of this expression? The equation can be solved by integrating. So, theta dot t is going to be let us say a constant C1, and then if you further integrate is and if you further integrate this becomes theta t equal to C1 t plus C2. These are two arbitrary constants, integration constants, and they can be obtained using initial conditions. Okay, at t is equal to 0, the initial conditions are theta at t is equal to 0 is theta naught, and at theta dot t is equal to 0 is theta naught dot. And now, if you substitute in these two initial conditions, theta naught dot is equal to C1 and theta naught from the second equation, which is this, you get this as C2, which actually then gives me the final expression of the response theta as a function of time t equal to C1, which is theta naught dot t plus C2, which is theta naught. Okay. That is our the final solution of this particular case, when the numerator actually is exactly equal to 0. With that condition, the response is this. Now, look at what this response tells us. Now, this response tells us that if our initial conditions are theta naught dot equal to 0, that means the initial velocity, I suddenly if this bar rod is standing straight vertically up, and then if I do not give any initial velocity to it, but I give some initial displacement, angular displacement to it, which is theta naught, which may be, let us say, if I disturb this and gradually tilt it by an angle theta naught, any angle, maybe let us say 10 degree, 20 degree, then in that case the response subsequently, after I displace this by an angle theta naught, the subsequent response theta t obviously is going to be just theta naught, which means that the bar will simply tilt and remain tilted at that point, at that position. Nothing will happen, neither will it oscillate nor will it continue to travel. That is going to be the equilibrium position. The bar is going to be in that equilibrium position forever after time t is equal to 0, right. However, if instead of giving any angular displacement to it initially, if I perturb it by giving some initial velocity, some initial angular velocity theta naught dot, that I just tap it with some initial velocity, and if that happens, then theta t is going to be omega t, which actually means that the subsequent angular displacement of this bar is going to continuously grow with time. Okay. It is going to rock, or it is going to swing continuously as t progresses. It will continuously go forward. It is going to rotate in the clockwise sense, depending upon, of course, in which direction the initial perturbation velocity I give it. So, which actually means that it is, the springs are not good enough to bring it back to its original equilibrium position. So, the vertical rod is going to just fall like that, and it is not going to return, which is the condition that we always relate to in a simple vibratory system, that there is a continuous interchange between the kinetic energy and potential energy. The mass travels back and forth continuously, moving about its mean equilibrium position. For this case, the mean equilibrium position assumed was vertical position. So, this is a case of a system that is getting unstable. It is not reverting to its original equilibrium position. So, the motion continuously grows with time. Let us take another, the third case actually now in this case, wherein this k L1 square plus L2 square minus mg L by 2 is actually less than 0, which actually means that the numerator goes negative. Okay. So, in this case what happens, which actually means that the squared natural frequency is a negative quantity. You can see that if the numerator is negative, if I square this, omega n square is going to be a negative quantity. Okay. So, I assume this omega n square as, let us say, alpha square. Okay. And then what happens, I have the expression here as theta double dot minus alpha square theta equal to 0. Okay. So, just have a look at this particular expression that we have written as a general expression, which actually should have been, I mean, if I write this as theta double dot plus omega n square theta equal to 0. This is quite similar to the expression mx double dot plus kx equal to 0, then we can write this as x double dot plus omega n square x equal to 0. Now, in this case, this omega n square being a negative quantity, I am writing this expression, as this. Now, how do we solve this? We know that I can assume a solution of theta as let us say a e to the power s t, the root s is assumed, and then obviously this theta double dot will give me s square a e to the power s t. We did this in the in this undamped vibration case earlier. So, now I can write this as s square, and you can show that this is going to be the equation that we would get, and which means that s is equal to plus minus alpha. Okay. And now if the two roots are given by these, S1 is plus alpha, maybe S2 is minus alpha. So, the general solution that I wrote here is theta t equal to a e to the power S1 t plus b e to the power S2 t, which actually means that a e to the power alpha t plus b e to the power minus alpha t. There are two roots, plus alpha and minus alpha. So, this is how the equation turns out to be. Now, usual things in the sense that I would like to get the expressions for a and b the way we do. This is done by implementing the initial condition. So, this is a alpha e to the power alpha t minus b alpha e to the power minus alpha t, and then these two equations substituting the initial conditions that at theta t equal to 0 is theta naught and theta dot t is equal to 0 is equal to theta naught dot. Okay. Then what happens is that I get the first equation gives me 0 equal to a plus b. Okay. This equation gives me a plus b equal to 0 because theta naught, and using this equation theta naught dot gives me a minus b into alpha. Okay. So, using these two equations we can get expressions for a and b. Obviously, a plus b is theta naught and a minus b is theta naught dot by alpha, right. So, let us say if I write this a minus b equal to theta naught dot by alpha, then if you add these two expressions we have a equal to half of theta naught minus theta naught dot by alpha, isn't it. So, oh sorry, this should be plus, and you can definitely substitute for a in this expression to get b, and then of course b is equal to b will be equal to a theta naught minus a, and a itself is half of theta naught plus theta naught dot by alpha, right. So, that gives me b equal to half of theta naught minus theta naught dot by alpha. Okay. As expected, that is how a and b would look like. And now I can write the final expression of theta t, which is equal to if I substitute for a and b, I can write this as half of theta naught plus theta naught dot by alpha e to the power alpha t, because a is with alpha t, and then plus half of theta naught minus theta naught dot by alpha e to the power minus alpha t. Okay. Now, what do you infer from the response expression that we have got? Theta t is nothing but your vibratory response as t progresses under the implied or input initial conditions of angular displacement at t is equal to 0 as theta naught and angular velocity initial angular velocity at t is equal to 0. So, once you give these two initial conditions, the response is given by this expression. Now, look at what the expression that we have got. Let us first figure out what do we infer from the second part of this expression. The second part tells us that no matter what theta naught and theta naught dot is, the multiplying function here e to the power minus alpha t, where alpha we have seen is a positive quantity, which means that this is exponentially decaying term, and as t progresses this particular multiplying term is going to be reducing with time, and therefore, no matter what the amplitude here turns out to be, whether positive or negative, this response is going to become 0 as time progresses. So, there is no problem from the second term actually, but the first term here, so depending upon the value of initial displacement or initial velocity, even if one of them is there or both of them are there, the response is going to grow. Why? Because the multiplying quantity here is exponentially exponentially increasing. The multiplying term here as e to the power alpha t is having a positive multiplying component to the t, and then therefore, as t progresses, the exponentially increasing amplitude is going to be expected. So, which actually means that when this particular condition is satisfied, then you have an unstable vibratory response, right, unstable irrespective of what initial displacement or initial velocity is, which actually means here that if the rod is disturbed, it will continue to move as time progresses, right. So, therefore, this is the case of an unstable vibratory system, that the with whatever initial conditions that you give, theta naught or theta naught dot, the response is always going to be unstable response. Okay. This is the concept of stability in this particular context, even in case of the undamped vibratory system. Let us now also look at how we can use this energy method in solving some other practical examples, and maybe before we take up another practical example, we will try to see how the effect of mass of the spring influences the natural frequency. Okay. We have been assuming that when we write the governing equation or generate the governing equation for such a simple spring mass system, we often assume that this spring is massless. Okay. So, we always say that the mass that is supported by the spring is heavy enough or much higher in terms of its inertia property compared to the mass or inertia of the spring itself. Right. So, in that situation, yes, many times the contribution from the spring mass may not be significant, and the natural frequency obtained may be accurate or practically quite close to the real value. However, suppose if the springs are having significant mass, how do I account for the spring's mass in obtaining a more accurate estimate of the natural frequency? Because whatever we say, actually if the mass moves and oscillates with certain velocity, the entire spring is also moving. So, each of the elements of the spring also has some kinetic energy associated, right. So, apart from storing the potential energy or strain energy because of the stretch in the spring element, it can also store some kinetic energy. The mass which is supported by the spring, it is in comparison to the stretch in the spring, the mass is definitely is always considered rigid. So, there is no strain energy stored in the mass simply moves like a point mass. So, it makes sense to consider the kinetic energy completely focused or completely concentrated in the mass, and the springs are typically massless. But supposing if the springs are not to be considered as massless, how do I consider or include the effect of the mass of the spring? So, for that let us assume that the mass itself is having a velocity, let us say equal to v, at the end of the spring here, that is of the mass itself, and you would agree that the velocity will keep dropping to the point of contact with the ground of the spring. So, the velocity of the spring is going to be 0 here, and it will be having a maximum velocity here. Similarly, that if I show the displacement, then the displacement is going to be maximum at this end of the spring, and it will be 0 here. So, we can assume a linear displacement profile, which means that if the displacement here is 1 unit, it will keep on gradually reducing. Each of these individual spring elements will have a displacement linearly related to its position from the ground, position from the fixed point. So, let us assume a small elemental length of this spring, which I will define as this spring's small elemental length dx of the spring, positioned at a distance equal to x, let us say from here, okay, and the velocity of this mass is v at its end of the spring. And we assume a linear variation of this velocity and displacement both. What will be the kinetic energy, a small elemental kinetic energy of this element dx? It will be equal to half the mass of that element dm times the velocity at that particular point. So, if I call the v at that position x as the velocity of that spring element dx, this becomes the elemental kinetic energy of the system of this particular spring element. Okay. V at this position would be different than this v. V is the maximum value or the instantaneous v at the tip at the end, and that itself is the velocity of the mass. Now, if we assume linear variation, then I can write this as half of dm. I will write as the linear mass density times dx, that basically is the mass of this small element here of the spring, and Vx I can write equal to V times x over L. L is the total length of the spring. So, this is the total length of the spring. Okay, and squared, of course. So, this element the a differential kinetic this kinetic energy of this differential element is going to be now half of rho L V square x square by L square dx, and this kinetic energy of this small element will keep changing. So, if I consider this small element, the kinetic energy here will be much larger. It will be large because the velocity is changing all the way from the root towards the free end of the spring or where the mass is attached. So, if I want to know the total kinetic energy of the system, if I call this as Ke, it's we will have to integrate this dk, which for the entire length of the spring. So, which is going to be 0 to L half rho L V square x square by L square dx, and that we can show that it is equal to half rho L V square over L square x cube over 3, and of course, if you solve this you will get this as half. Now, rho L into okay, so rho L and V square L upon 3. Okay. So, rho L into L itself is what? The mass of the spring. So, half rho L into L is the mass of the spring times V square, and that is divided by 3, right. So, what we can see here, that if you consider only the spring itself has its own kinetic energy, and that kinetic energy is given by half of mass of this 1/3 the mass of the spring times the square of the velocity of the mass. So, if I now want to consider both mass as well as spring, the spring has its own stiffness, but it also has its own mass, and the mass supported by the spring is capital M, then it is quite clear that the total kinetic energy of the system, consider the kinetic energy of the mass plus that of the spring, this is going to be half m let us say x dot square, if this is x and x dot, plus the kinetic energy of the spring, if I call this as k E s, is half m s over 3 x dot square, because x dot we considered as v. So, which basically tells me that if I want to now write the natural frequency of this single degree of freedom system, but considering the mass of the spring, is going to be k over m plus m s over 3. Okay. You can easily show using this expression of kinetic energy and the potential energy stored in the spring. It is a straightforward to show that the natural frequency expression turns out to be this, which actually means that if I want to add or include the mass of the spring, we need to include 1/3 of its mass, and the reason why it is not full mass, because each element of the spring has a different velocity when it is oscillating, and therefore it can it so happens that the entire spring's contribution happens to be 1/3 of its mass contributing to the kinetic energy. Is that clear? So we use this expression of kinetic energy. Maybe if I also show the potential energy expression here, the spring stiffness multiplied by x square, that is your, sorry, wait a second, this is the potential energy or strain energy in the spring. So, if I write this as d dt of v plus t equals 0, it basically means that it is half k s x square plus half m x dot square plus half mass of the spring x dot by 3 x dot square equal to 0, which if you solve, you will get the governing equation as m plus 1/3 of m s, okay, x double dot plus k s into x equal to 0. That is what you will get by solving this equation, which again will mean that you will get this expression of its natural frequency, right. So, this is the second example, basically to highlight how the spring mass can influence the natural frequency value. But you must notice here that only 1/3 of the mass of the spring contributes, and usually the mass of the spring is not very significant, but if you want to have a very accurate value of the natural frequency, maybe you can include the mass of the spring. Okay, so the next example wherein we will again implement the energy method to obtain governing equation of motion and expression for natural frequency is the example here for a rocker arm tappet valve mechanism. So, the example here is it says that the idling speed of a 4-stroke IC engine is 550 rpm. A cam follower system is used to is used for fuel control valve, which is this, and the push rod is excited by the cam mounted on the camshaft. So, this is your camshaft and this is the cam that rotates. We all know from our dynamics of machine, theory of machines course, how the cam shaft is connected to the main engine shaft and how it operates at half the speed of the engine and how it operates the valve to let the fuel into the cylinder. So, this push rod is being pushed by the operation of the cam, the rotation of the cam. It sort of uses the leverage that we get here in operating the valve in the cylinder against the spring pressure. So, this is the spring, the coil spring, which is connected to the other end of this rocker arm here, and it is fixed to the cylinder head. Okay. So, the spring is fixed at its one end here, and at the other end it is just butting against the rocker arms one end. The other end, the push rod is butting here. So, the push rod pushes the rocker arm, it rocks. So, obviously, the degree of freedom that we can consider here as theta, and we are supposed to ensure or probably find the spring stiffness, so that there is 20% separation margin for engine idling speed from possible resonances. Okay. Now, we will come to this point shortly. What does that mean? But first, if this is the vibratory system that we are supposed to analyze, our first step of vibration analysis tells us to get a simplified vibratory model. Okay. This is a physical system, of course, sketched in a very simplified way, but still it captures its motion characteristic. So, this rocker arm has some mass and its mass moment of inertia is given. So, if I want to now treat this as a vibratory system, what I can definitely say is this lever, which is fulcrumed here, is the main inertia of the system. Of course, this push rod can be treated like a spring. The push rod is long enough, it is flexible. So, you already have the spring stiffness given of the push rod. So, not all the time you should not all the time all the structural elements will show up like a coiled spring. So, this rod, which could be a circular one, if it is slender one, it will have its own longitudinal stiffness. So, this itself can be modeled like a spring, but it is not a normal spring. We just saw how the spring's own mass can influence the natural frequency. So, by giving the mass of the push rod, we can, if we want to, consider the mass of the spring in the analysis. At the other end, what is happening is that this valve is connected to this end of the rocker arm. So, there is a valve which is like a cylindrical piece with a flat valve at the tip, but as the rocker arm moves in the angular direction with angle theta, the valve simply gets pushed up and down. So, whatever is the vertical speed this rocker arm end has, let us say if I call this as V, the same velocity will be that of the valve. The valve has been given with a mass 0.25 kgs. So, it in a way kinematically it can be treated like a lump mass itself attached to the end of this rocker arm. So, this valve, the velocity of this valve, for the sake of considering its contribution to the kinetic energy of the system, we can as well consider the valve mass to be situated here, because the velocities, whether you consider it here or here, is going to be identical, except of course, if the valve itself deflects. Now, if it deflects, then it is not the case, but we have been given that that the valve is rigid, in the sense that there is no flexibility in the valve. All the flexibility that you have is in the spring here. So, at this end there is another spring which is fixed to the cylinder head, and this spring is having the spring stiffness let us say Ks, as you see here. The spring also has its own mass. So, in this case there is a mass of the spring as well. There is a mass of the push rod, and then there is a stiffness of the push rod. So, now you can see that it is a very simple simplified model of this apparently a more involved kind of a vibratory system, a push rod, rocker arm and valve all connected to each other. One of the simplified model is now this. So, it is like this spring is attached to the end of this rocker arm, this spring is attached to this end of the rocker arm, and the only degree of freedom now we can consider is the rocking motion, the angular oscillation theta. There is no other degree of freedom here, as you can see, okay. And all the motion that you are seeing here, this motion and this motion are actually related to the angle theta. So, even if we consider the motion here as y and here as x, they are connected to theta. So, based on the lengths of these rocker arms, if I call this as L1, which of course is given here, and this as length L2, the rocker has these two arm lengths L1 and L2. So, what we have done is, from a physical mechanism, rocker arm mechanism here, for operating the valve of for letting the fuel in the cylinder. So, there is a cylinder over here, and through the opening of the valve, the fuel is let in, and that opening of the valve is governed by the camshaft's operation. So, this entire physical system is now converted into a simplified vibratory model, which is an oscillating rocker arm here, fulcrumed here, with a spring attached at one end and another spring here at the other end, and the only degree of freedom we are accounting for is theta. Now, what is asked is not only getting the governing equation or solving for natural frequency, but it is almost like a design exercise. The design in the sense, although the spring stiffness is given here, what we have to see that if the spring stiffness is considered as 10 Newton per millimeter, then is there a 20% separation margin for the engine idling speed. Now, since we have accounted for only 1 degree of freedom here, it will give us one natural frequency omega n for this vibratory system. Separation margin means we already know that when you plot the response versus the operating or excitation frequency, we get a resonance like this. Okay, this frequency is the excitation frequency, and what it is asking us to check whether with this spring stiffness, either you find out which is the required spring stiffness, or if the spring stiffness is considered, whether we shall be at least 20% away from the natural frequency or resonance, right. So, whether using this spring stiffness, are we going to lie either in this region or in this region to avoid closeness to the resonance region. That is what the separation margin is all about. So, this gap should be 20%, or the frequency difference between the natural frequency and the excitation frequency should be 20% of the natural frequency. Now, how does it relates to engine idling speed? Because if we are idling at a particular speed, let us say 550 rpm, which is given here, which means that let us say I am operating at this particular position, which is 550 rpm, and the natural frequency may be somewhere here. I will have 20% difference in the two speeds, and then I will be safer. Okay. So, the natural frequency that I get by using this value of the spring stiffness should be 20% away from the excitation frequency 550 rpm. However, there is a catch here, it is the engine idling speed, it is not the camshaft operating speed, which actually means that if I operate at 550 rpm, the camshaft operates at 220, so how much will it be? 225, sorry 275 rpm. Okay. So, the camshaft will operate at 275 rpm, and therefore, this speed will have to be accounted for as 275 rpm to account for the fact that camshaft operates at half the crankshaft or engine speed. So, using this case, what you will have to do is, first once you get the governing equation and get the natural frequency expression, you will substitute all these values and check whether the natural frequency for this system turns out to be either 20% away from this 275, either on this side or on this side. This side is preferred for a simple reason, that this is the lowest speed with which the engine will operate. Otherwise, as you raise your engine speed, the speed is going to be increasing from 550 rpm onwards at a higher speed. So, if you can ensure that it is on this side of the 275, it will be safe for all the other higher speeds of the engine crankshaft. Alright, so with this background, let us at least get the governing equation and expression for natural frequency. Then of course, one can substitute all these numerical values in the expression to get the frequency value. Now, if we want to do that, we will have to get the expressions for the kinetic energy, potential energy, the way we found in the previous cases. So, if this is modeled like a rocker fulcrumed here, okay, and there is a spring which is that of the push rod, there is another spring here which is this particular spring, and then of course, I am considering theta as the degree of freedom. Okay. Now, what is the process for getting the governing equation? Free body diagram has been obtained. This length is L1, okay. This length is L2 as we discussed, and the mass moment of inertia of this rocker arm is J. This is the spring of the push rod, it also has the mass, So, MP is the mass of the push rod, spring and the mass of the spring, and then of course, there is a mass of the valve here. So, mass of this valve, okay. Either you consider it here or you can as well consider it here, but then please make a note that the spring is around that valve. So, it is not in series with the valve, okay. It is parallel to the valve. So, the valve can operate up and down with the same velocity as the tip or the end of this particular rocker arm. Okay. Now, let us consider the expression for the potential energy. How is potential energy, total potential energy of the system to be obtained? All the energy that is stored in the spring elements. Now, the springs are two here, one is the push rod. So, although you do not see geometrically there is no spring as such, but this thin push rod itself acts like a spring, and the spring stiffness is Kp. So, half Kp into so if this displacement is assumed as y of t and this as x of t, okay. So, you can consider this y of t and x of t as the two displacements at the tip of this of the rocker arm, then half Kp into y square, okay. This is the strain energy that will get stored in this spring, okay. So, you add to that the strain energy stored in this particular spring, the rocker arm being rigid. So, half of Ks into x square, okay. X is the instantaneous deflection in the spring. Now, you can see that this x can be written as L2 into theta and y can be written as L1 into theta, is not it. So, although you show these two displacements as two different ones, but they are not, actually they are geometrically related to the assumed degree of freedom, that is theta of the rocker. All right, we will do that later, but maybe I can write this as Kp into L1 theta square plus half Ks L2 theta square. So, maybe that is the revised expression of the potential energy. What about the kinetic energy, capital T, in the system? We already have seen that there is a mass of the push rod that is assumed, right. So, if the push rod mass is to be accounted for, okay, but that mass is distributed, okay, it is not a lumped mass as such, okay. There is a difference between the mass which is distributed of the rocker and that of the push rod. The push rod is getting compressed and it is moving. Each of these elements move with a different displacement as compared to this end of the push rod. So, each element of the push rod moves with different velocities, right. So, therefore, this is almost like a spring and we have discussed enough in terms of considering the mass of the spring. So, if that is the case, then the kinetic energy contribution from the push rod is going to be half mp into y dot square, but the mass of the push rod is reduced by reduced by to 1/3 of its total mass. That is the effective contribution of the push rod, okay, to the kinetic energy. We have seen that if the spring and mass is there, if mass of the springs is to be accounted for, its contribution to the kinetic energy will be 1/3 of its mass. Okay. Now, what else you have next in the line? The rocker arm. So, that is a rigid rocker arm and therefore, the kinetic energy of the rocker arm is J theta dot square, that is the kinetic energy of the rocker arm, followed by what do you have here at the other end of the rocker arm on the right hand side, you have a valve which is getting pushed. Okay, that valve is not getting compressed, so it is assumed rigid. So, the mass of this valve, the cyan colored valve rod that you are observing here, that will contribute without any change, right. So, mass of the valve times what? X dot square. So, the velocity of the valve at the tip here and at this point are identical, okay, does not deflect. So, the value of the velocity is the same. So, half of mv into x dot square is the kinetic energy of the valve. But you also have the mass of this spring to be accounted for. The spring not only contributes to the potential energy term, strain energy, but also contributes to the kinetic energy. So, I will add here the contribution from the mass of the spring, valve spring here, by taking 1/3 of its mass, and then you have x dot square here. Is there anything that we missed? So, all parts are accounted for. You have push rod accounted for, you have a rocker arm accounted for, you have a spring accounted for, and you have valve accounted for. Out of these, the rocker arm and valve are already declared as rigid. So, therefore, they did not contribute into the the potential energy expression, but we looked at the flexibility in the push rod and the spring in figuring out that their own masses will contribute to the kinetic energy, but not in full. Okay, 1/3 of their masses will contribute. Now, once we have obtained these two expressions, one for the strain energy, the other one for the kinetic energy, the next step is absolutely straightforward and very simple. And so, this is the expression that we already got, the total kinetic energy, potential energy obtained. And now, what you can do is, because it should not confuse that x and y are the 2 degrees of freedom, they are not. The only degree of freedom here is theta. X and y are related to theta through the lengths of the arms, and therefore, if you substitute y and x into these two equations and then apply the conservation of energy, that is the time derivative of total energy is 0, you will find the expression for the governing equation. Okay. And the expression which I have highlighted here is obtained like what you see here, right. So, Kp, Ks, the push rod stiffness and the spring stiffness appears in the numerator, and the mass of the push rod, that of the spring, that of the valve, and of the rocker arm inertia, they all appear in the denominator as we expected. So, that is how the natural frequency expression has been obtained. So, if you really look at the overall vibration analysis process, we first looked at this physical system, considered all the possible motion, and we figured out that only degree of freedom here is theta, and then accordingly we got the simplified vibratory model. We used energy method in this case instead of Newton's approach or application of Newton's law to get the governing equation of motion and get the natural frequency expression from that. Once you do that, we have to do inferencing, right. That is what we said. Once you get to solve for natural frequency or vibrationary response, how do we make sense out of this outcome, right. So, I would suggest that you use the numerical values which are given in the previous slide to obtain the value of omega n, and then what has been asked or what has been indicated in the example is that either you find the value of the spring stiffness here Ks, so that this resonance is kept 20% away from the engine idling speed. Now, we have seen that if the engine operates at 550 rpm at its idling condition, the camshaft will operate at 275 rpm, and it is the camshaft that is pushing this entire vibratory structure or exciting this vibratory system. So, for me the excitation frequency omega is going to be 275 rpm. Now, this of course will give you in radians per second, you will convert that into rpm, and this omega n, whatever you get by substituting all the numerical values, will be this value. And what you are supposed to check is that whether this gap between the natural frequency of this vibratory system and the excitation frequency for this vibratory system is whether those frequencies are away by 20%. It is preferable that the natural frequency lies on the left of this rather than figuring out that your 275 rpm is here and the natural frequency is on the right side. Why? Because as the engine picks up its speed, it will anyway then again cross through that resonance region. So, it makes more sense to consider the spring to have a stiffness in such a way that the natural frequency lies on the left side of it. That is how the outcome of these natural frequency expression and the values should be interpreted or should be considered in the vibration based design of the mechanical system. Okay. Can we solve this same expression and governing equation using the Lagrangian equation? Yes, I think that is left to you as an exercise. Let me remind you that the expression, the Lagrange's equation is given by this. So, if I want to apply this to the existing example, the time derivative of dou t over dou x I is nothing going to be dou t over dou theta dot. Okay. So, you will have to first take the time derivative of this kinetic energy with respect to theta dot, derivative with respect to theta dot minus dou t over dou theta, because our generalized coordinate is theta, and then plus dou v by dou theta equal to 0. Can we do that now? If we suppose try to get apply this Lagrange's method, let's find out what the expression gives us if we apply that. So, if we take this derivative, I'll write this as dou t of dou t over dou theta dot. Now, the expression for t is here with respect to theta dot. If I take the time, if the derivative of this is obtained with respect to theta dot, then I get what? Half mp over 3 and then L1 square 2 theta dot. Okay, that is what you will get if you take the derivative with respect to theta dot. It will not turn to theta double dot here. And then what? Plus half 2 j theta dot plus half mv L2 square 2 theta dot plus half ms over 3 L2 square 2 theta dot. That is what you will get as this particular term in the Lagrange's equation. And the second term says that dou t over dou theta. Now, please make a note that this expression does not have any theta in its in its terms. So, this value is going to be 0 for this case, and plus dou v by dou theta, which means that you find out what is the derivative of this with respect to theta, and then of course, I can get this as half k p L1 square 2 theta, okay, and plus half Ks L1 square 2 theta equal to 0. And now if I take the time derivative of this expression, then what? Then I get mp by 3 L1 square plus theta dot will change to theta double dot plus j theta double dot, all right, plus mv L2 square theta double dot plus ms over 3 L2 square theta double dot plus Kp L1 square theta plus Ks L1 square. I think this should be L2, this is a printing mistake here. So because x is L2 into theta, so pardon me for this small change here. This has to be Ks into L2 and not L1. So that gives us Ks into L2 square into theta equal to 0. That is what the equation that we finally get. But if we bring in all the terms in theta double dot together, then I have j plus mp over 3 plus ms over 3, mp into L1 square, and then this becomes ms into L2 square and plus mv into L2 square theta double dot plus Kp L1 square plus Ks L2 square into theta equal to 0, which is in a standard form of mx double dot plus kx equal to 0, which gives us the expression for the natural frequency as Kp L1 square plus Ks L2 square over j plus mp over 3 L1 square plus ms over 3 L2 square plus mv L2 square. Okay, that is the expression I have. You expect the same expression, and that is, I guess, is what we are getting here. So, to summarize this lecture, we had a good introduction to the energy based method as an alternate to the Newton's of law based method of getting the governing equations of motion. And within the energy methods, we explored several alternatives. The ones which are used more are the conservation of energy, where we take the derivative of the total energy to be equal to 0. With that, we can get the governing equation of motion. Alternatively, Lagrange's equation, as I mentioned, is a more classical way of getting the governing equation of motion, and hence for a simple case an expression for the natural frequency. We discussed a couple of examples and saw that if we include the mass of the spring in getting the expression for the total energy, the spring mass can contribute to the natural frequency. Okay, these are the questions related to today's lecture, and a very simple question on the energy method. So you may now have a go at these questions, try it out yourself, and then verify your answers with the answers given in the next slide.